Our next presentation comes from Dr. Andrew Gettelman. Excellent. Dr. Gettelman's a senior research scientist in the Climate and Global Dynamic Division at the National Center for Atmospheric Research. His presentation today is going to be about COVID contributing to the counterintuitive climate change.
Well, thank you very much. Now, are you seeing the regular presentation, hopefully? Or are you seeing the presenter view?
I see I see regular presentation.
Regular presentation. Good. Okay. Well, thanks very much, Brian. This is going to be a really interesting tag team with what Greg just did, because you better hang on, because I'm going to jump about 10 to the 15 orders of magnitude from the nanoscale to the global scale. And this is the opposite side of what COVID's done. This is the macro scale view of what COVID's done to our environment to some extent. And as Brian said, I'm at the National Center for Atmospheric Research, and this is work I did. I was actually on sabbatical in the UK when this whole thing started. And so this is work I did with some colleagues in the United Kingdom and back at NCAR. So most of us have experienced changes to our mobility in the last year or so. And this is a chart based on mobility trends and changes from Apple devices. You can see a weekly cycle in here of things jumping up and down, but you see a sudden change last spring when all over the world, people stopped moving around. And that picked up back in the summer and people moved around more. And now there's been more lockdowns in other parts of the planet, and that's changed again. So there's been dramatic moves by as much as 60% in how people's actions have changed and how our mobility has moved around. And that leads to changes in emissions and changes to the environment. So many of you have seen the anecdotal pictures like the ones on the right. This is Delhi in October of 2019, a bunch of people walking around, nobody walking around in April. And the sky is also a lot cleaner. Now that's a little anecdotal, it's not statistical, but if you look a little more statistically, on the left, you see some data from China, and the circle in the middle there is kind of where Wuhan is. This is nitrogen dioxide. So this is essentially, nitrogen dioxide is a byproduct of the emissions of combustion of fossil fuels. So this is a measure of internal combustion engines, really. And you can see the dramatic drop in nitrogen dioxide over China between 2019 and 2020, which is due to the early lockdowns that occurred there. There are other implications of that as well. So this is a recent picture from Boulder, Colorado, which I haven't seen in a while. This is contrails from airplanes. And of course, there were probably no other sector was quite as much affected as aviation. This is data, again, the peaks are a weekly cycle over the course of the year. In total air traffic movements over time, and you can see steadily from the blue up to the red, a rising trend as air travel gradually increases. And then you can see 2020, which started out in purple as being higher than any other year, and then suddenly dropped off to something like a 75% reduction. It's since recovered to about 80 or 90% of where it is, but that also changed the environment around us. So what do these things all mean for climate? And in order to walk you through that, I'd like to talk first a little bit about, get everybody on the same page about what climate and climate change is, and sort of distinguish climate from weather, which will be important from understanding the effects of weather from the effects of emissions changes. Talked a little bit about the COVID changes on emissions. I'll talk a little more specifically about that. And then we'll actually show you, this is sort of the HPC part about how we estimate COVID effects on climate. And then the conclusion of that is that reductions in emissions due to economic activity changes actually probably warmed the planet a tiny bit. But I'm going to close with what this unintended experiment actually tells us about potentially how we can start to do something significantly about climate change. And I think there's some interesting lessons in the pandemic for that. So just to get everybody on the same page, somebody once said that climate is what you expect, but weather is what you get. And you can kind of see that. This is the climate in Madison, Wisconsin, as expressed as the minimum temperature on every single day in January in the 20th century. And it's a distribution of all possible states. And the coldest day in the 20th century was January 30th, 1951. It was minus 40 centigrade. That's about the same in Fahrenheit. It's so cold. It's minus 40 Fahrenheit. But climate is the overall distribution. Weather is chaos. Chaos theory was actually developed by a meteorologist, Edward Lorenz at MIT in 1961, and it explains why the weather is not predictable beyond a certain point. But climate is this distribution, and climate is the distribution of possible weather and its probability, and climate is actually predictable. So when we think about the weather, we can predict a week, 2 weeks maybe 3 weeks in advance, but then we're really starting to look at the climate beyond that. So climate change is taking that distribution and shifting it. And so you can see, you talk about a existing climate, which has some record cold weather in blue, that's low probability, and some a little bit of record hot weather in red, which is a low probability. And if you take that whole distribution and shift it, say with respect to temperature, suddenly the area under that curve, which is the probability of getting any given value, for temperature, it gets much larger, and you get much more, you get exceedances of previous records, and you also get much higher probability of exceedances. So this might be fine if you're in Madison, Wisconsin, if it gets a little warmer. It's probably not fine if you're in Phoenix or Amman, Jordan, or somewhere like that. You can start to get to climates that start to be uninhabitable. And you can make this curve for any sort of variable. You can make it for precipitation, for example, which would be very important. So what did the pandemic actually do in terms of, mostly it didn't really affect the weather, but what did it do to our emissions that we can then look at the climate impact of that? Well, pollution is associated with transport and industry, and there were lots of changes to initially industry and then continued changes to transport. This is, again, a picture from March, averaged over India, 2019 on the left, 2020 in the middle, and the anomaly. And this is aerosol optical depth. So it's a measure of the total amount of particles in the atmosphere. It's essentially the haze in the atmosphere. So you can think of the 2019 picture as the upper panel over Delhi with a sort of hazy sky. 2020 was a lot cleaner in general, and you can see that averaged over the whole month. The big blue stripe is the Ganges River Valley. There's several 100 million people that live in that one area, and that was a big change. But you can see it doesn't go down everywhere. Over the central part of India, you can see there actually were some increases in 2020, and that has to do potentially with just weather effects. So some of that actually has to be filtered out. I'll show some efforts to do that. Here's another effort to do that. So the bottom panel is the change in particulates now globally. So this is for January to May, not accounting for the weather, but it's averaged over a longer period of time. And you can see over India, all these purple dots, except for the little red in the south. So that's kind of what we saw before, just for 1 month. Lots of reductions over China, lots of reductions over Europe, not so many reductions over the eastern United States. And there are ways this study actually tried to account for the weather effects. So the particles are the upper right panel, and you can see most places there were reductions. What's interesting is that obviously there were reductions, as I showed, in nitrogen dioxide, which is on the left panel, which is due to transport use. But the panel in the middle, which is ground level ozone, which we commonly think of as being a sort of an irritant for lungs, it damages crops, it's sort of the prime suspect in air pollution. It actually increased a little bit, and that's actually due to complex air pollution chemistry, where if you reduce some of the sources of pollution, like the nitrogen from transport, you can actually cause increases in ground level ozone. And this is actually accounting for weather. So there's some definite offsetting complexities here. And hopefully this will play. So this is, again, looking at nitrogen dioxide, and it's sort of a visual thing that NASA's produced, showing what you're going to see is a bunch of little green lights show up on these stations, and those are actually lockdowns. So as we get into February, you see China locks down, and the blue means big reductions in nitrogen dioxide. If you go to Europe, then starting in March, you can see Italy goes into lockdown, lots of reductions in emissions, and then all of Europe goes into lockdown. And you can see a time series of this where, New York is actually already coming back as you see this as we get into the late spring. And if we go to the eastern United States, by the time you get into early summer of 2020, there's moderate reductions, but no lockdowns. And you can see that emissions have just about returned to normal in some cases in the eastern United States and the New York area. So there's lots of variability in this in trying to pull out this signal. See if I can advance the slides one more. There we go. And we can look at overall, I showed some of the aspects of air pollution. This actually shows what happened to our energy use due to this change in transport. And obviously, if you look at the energy use by sector, the green bar for oil, the third one down, that was reduced significantly, on the order of about 10% drop in use of oil. That's because it's primarily used for transport. What's interesting is there was also a drop in energy use in general in the coal, gas, and nuclear sectors. And that's somewhat due to changes in energy demand for people moving around less, not needing to heat office buildings, not needing to use electricity in a lot of those areas. But what was interesting is renewables actually increased. So there was the biggest drop in coal, which is the most damaging gas as far as it's the most it's the most damaging fuel because it's the most carbon intensive. So it produces the most CO2 per unit energy. So 5% loss in total energy demand, but actually slight increase in the use of renewables. That translates into about a 7% decrease in total carbon dioxide emissions, which is something like going back maybe 5 or 10 years in our total emissions. So it's not a huge amount. And you can see, obviously, the energy sector investment temporarily fell off pretty dramatically during that time. So interesting shifts in the electricity sector and in energy use occurred during the pandemic. There were some places where coal actually decreased pretty significantly. It's not a great fuel if you don't know your energy demand. Coal-fired power plants are kind of like a charcoal-powered barbecue. You have to get them going. It takes a while, and they have to be kept at a constant temperature and constantly fed to keep them efficient. Whereas gas power plants are much more like your stove. You can just turn them on and off. And of course, nuclear, if you turn them off, you're not bringing them back online for a while. So, but renewables was also very intermittent, and also the marginal cost of renewables is a lot cheaper because there's no fuel involved once it's installed. So if you don't know what your demand is, then it's easier to keep your renewables running because it's essentially free. That was an interesting change in the energy sector, which obviously is going to have some impacts on the environment with respect to CO2 emissions. Okay, so how do we model all this? This is sort of one slide on how we actually model weather and climate. They're actually very similar, but what I'll show you is the sources of uncertainty are different. So how you design simulations are very different. It's essentially just an accounting exercise constrained by physical laws. So if you take a grid all over the planet, and at each point on the planet, you define a spreadsheet of physical quantity. So think of a giant spreadsheets with entries for water, heat, wind, salt, carbon, pollution, all these different physical processes and physical states. You can account for each process that transforms water, for example, whether it's in the ocean, whether it's in the atmosphere, whether it's in a cloud, whether it's precipitation. We can describe that with basic physics. You can solve equations for these processes at each point. You balance all these spreadsheets for the motions of things and how they interact in time, and you can advance this in time, and you just repeat. Of course, you're dealing with millions of points on the planet, and you're trying to do it for time steps, which are minutes over the course of the year. So you have thousands or tens of thousands of time steps. So some of the common problems with this, in addition to the computational load, which limits the scale of the number of points we can deal with, is that when we're dealing with scales that are on the order of 60 miles or 100 kilometers for one of these little points, which still discretizes to millions of points on the planet, we can also only describe things like a cloud with one or two values. So the cloud on the left, which has complex distribution of its water properties, as you can see from the gradations and shading, might look something like the right. And of course, that's very hard to describe at the right scale. And we have to basically describe it in ways that are highly uncertain when we do this. So this is a lot of our uncertainty in our ability to model weather and climate. We talked a little about the difference between weather and climate. And one of the differences is where the sources of uncertainty come from. Remember, weather is what we get, climate is what we expect. The biggest uncertainty in short lead times for weather prediction are actually the initial condition. The biggest predictor of what the weather is tomorrow is what the weather is today, both at our location now and at, say, a location upstream or upwind of us, and how that will propagate downstream. That's actually the biggest initial condition uncertainty. If you're worried about what's the climate of 50 years, the initial condition doesn't matter at all. So it decays over time. What matters in 50 years is actually how much carbon dioxide is in the atmosphere, which we don't know, and we can't predict in the model because that's actually a human choice. It's a function of our policies. So we call that a scenario. That scenario uncertainty rises over time. And throughout this, there is model uncertainty. There's that inability to really describe the clouds and the other processes correctly. So these add up to the total uncertainty. And what it says is that we have a lot of uncertainty in the weather scale and a lot of uncertainty in the climate scale. And the climate scale uncertainty actually comes from scenarios and how much our emissions are going to change and how much society changes. And the short time scale comes from our initial conditions, what the weather looks like today. So again, we're dealing with the weather scale in the short term and the climate scale in the long term. So the sources of uncertainty are different. Again, weather's what's the weather today. Model is, say, how we represent the processes, and the scenario uncertainty, or what are the emissions of CO2, or how does COVID actually change things? So this is interesting how you deal with this in the weather context. So if you think of all the possible states, that picture of Madison, Wisconsin, and I'll get to this, where we start now is going to help us determine where we end up, say, tomorrow or in a couple of days. So we take a bunch of observations to try to constrain that state. But those observations themselves are uncertain. We don't exactly know the temperature, and we certainly don't know it at every point. We only measure it at discrete points. So we have an uncertainty in our present state. And when we run the model with slightly different versions of that current state, like different temperatures at different locations, we end up with a bunch of different results, which is what we call a probabilistic forecast if you add up the envelope of where those possible results are. And that's just a subset of the total climate. But it's sort of where we end up. If you just run it once, you get a single deterministic forecast. That may not be actually representative of the uncertainty. So this is a way to describe uncertainty in weather prediction. And we're going to use this in some of these simulations to talk about COVID. So how do we find small signals? We talk about a 5 or 10% reduction in something with all this weather noise that gets very difficult to sort out. Well, weather and climate models allow us to simulate the past and simulate alternative paths. So we can estimate the COVID reductions in emissions, and I'll show you some of that, from greenhouse gases, from aerosol pollution, even from contrails. And since these changes really wouldn't have changed the weather because they're in small and they're fairly short term, we can fix the weather state and run these different scenarios with different sets of emissions. We can do it for COVID and the COVID emissions we think actually happen, and we can do for estimates of what a normal year would have looked like. And then we can actually take those weather states and sample across small perturbations in those initial conditions. So this is something that high performance computing is really good for, because we can help define the uncertainty. These ensembles are just embarrassingly parallel. You change your initial conditions and you run your model simulation again. So instead of looking, as I said, at all the possible weather states, we're actually going to fix the weather states to, say, 2020. That's what January of 2020 might look like. And then we're going to try to look for changes in those states alone, not in every possible state. And that actually, it turns out, is a much easier problem. So the way we do this is, obviously, we're using some supercomputing to do this. We're using two Earth system models. One was run at NCAR on our Cheyenne computer in Wyoming. The other was run at the European Center model in Hamburg. That was actually run on some UK systems. It's interactive atmosphere and land model. We fix the ocean temperatures and the sea surface temperatures. And as I said, we nudge the meteorology. We sort of fix the weather state to 2020. We do this at about 100-kilometer horizontal resolution with complex clouds and aerosols to get all these chemical interactions and get all the appropriate interactions for the emissions. We actually do ensembles of 20 simulations with COVID reductions and with a normal year. We can actually difference these entire clouds of ensembles to actually get us some statistical significance on these points. And we're going to change emissions of particulates, aerosols, and contrails, and I'll show some estimates of putting in the greenhouse gas emissions too. So these are actually fairly straightforward simulations that are made possible by the tremendous capability of HPC. So we're dealing with a moderate scale system. It's an SGI system with 145,000 Intel Broadwell processors, 5.3 total petaflops. Each of these simulations is using about 800 cores. For 20 of those, blowing them through at the same time, we're only using about 15% of the machine at its peak for something like 2 to 3 hours for each of these sets of ensembles. So these are not large or heroic simulations. These are organizing and taking advantage of this embarrassingly parallel aspect of the systems. They're all analyzed. We get about 4 terabytes of data out of this that we can process down to 40 gigabytes and take a look at. And again, as I said, these are sort of everyday simulations, I would call them. And then we can also put all these things together with a simple emulator of climate models at the end that kind of puts it all in perspective. So this comes from a colleague at Imperial College, Robin Lambaugh, who took those mobility trends and used them to modify the standard sets of emissions to estimate what the changes would be. And the advantage of using mobility trends is we have a consistent data set for most countries on the planet that's geographically sort of aggregated by country. So you can actually then make changes over time and by location. So the global totals are shown on the left. You see this big reduction in April, and these are maps for April showing reductions in black carbon. You see big reductions over China and India. Volatile organic compounds, which are one of the main aspects of air pollution, And you can see reductions over most of the industrial world, and particularly over India and China, and also into Indonesia. Carbon monoxide is produced, carbon dioxide and nitrogen oxides are produced again from fossil fuel burning, and those patterns are somewhat similar. Nitrogen oxides are also produced from ships, and you see shipping lanes showing up from the diesel engines on ships, which don't have any emissions controls, except they have emissions controls around the coast of the United States, which is why you don't see a lot of nitrogen dioxide emissions in the ocean around the US. So you can see a lot of things coming out. These are the estimated changes in these quantities that we can then put into the model. We also can look at aviation emissions. So on the right is a map of aviation water vapor showing all the various flight tracks. That's at flight altitude. Again, this flights by year map that I showed you with the big reductions in 2020 in the purple, and those data can be combined to actually give us a scaling, which is the fractional reduction in aviation, which peaks at about 70% of aviation emissions in the spring of 2020, and then increases back to 80% by the end of 2020. So we can put all those things into these Earth system models, and these we can actually show that we get a small impact of these COVID emission changes. We see reductions in aerosol optical depth, and again, you see the clouds of points, which indicate these are significantly different than zero across these different ensemble differences. But we see reduction in aerosols is actually associated with an increase in net energy, and that is about 10% of the total effect, which more than offsets, as I'll show you, any decrease due to CO2 reductions. So cleaner skies may have actually warmed the planet, and the reductions in contrails, because contrails warm the planet, actually cooled the planet a little bit, but that was slightly smaller. Just to show a map of this, the top two panels, the left is radiation, and the right is the temperature difference in May, and the bottom is for the other two different Earth system models, the bottom row. So you can see these reductions happened. Again, the reductions in emissions were mostly in the Northern Hemisphere. The cleaner skies were mostly in the Northern Hemisphere. The warming temperatures reached up to something like 0.4 of a Kelvin at some points in the Northern Hemisphere, particularly over higher latitudes of North America and over Asia in both of these models. The global average effect is actually very, very small, and I'll show that in a minute. The contrail effects in these scales are slightly different. You can see the reduction in the ice water path, so the amount of ice in the atmosphere in the upper left, that led to and there are decreases in the ice number concentration. That led to decreases in high cloud fraction on the lower left. That actually led to a cooling of the land surface. These high clouds of contrails actually are a net warming. That scale is about a third of the scale on the previous plot, so this is actually a smaller effect. So putting it all together with a simple model, so we can put all these forcing changes, essentially the radiative effect together with the CO2. The radiative effects are shown on the on the left. And this is a simple model that allows us to look at the relaxation time of the full coupled system like the ocean. So what you can see is reductions in contrails in red give you a small cooling effect. If you look at the temperature change on the right, the biggest response is the aerosol. So these reductions in aerosols and pollution were actually a warming effect, and the total actually is a net warming effect. The CO2 effects are actually fairly small. Those are indicated in that orange line, but they persist over time. So the net effect of all these changes, essentially us slowing down and cleaning up the planet, was actually a slight and temporary warming because of these aerosol effects. You can see the CO2 effects last an incredible amount of time because CO2's lifetime in the atmosphere is on the order of 100 years. So what does this all mean? Well, air quality improved in many ways. The particles and the nitrogen dioxides were reduced. Ground level ozone did not actually decrease due to the complex chemistry. The global climate effect was small. That's about 0.03 of a degree. That's about 1/3 of the annual, the variability in that number from year to year. But interestingly enough, 2020 was tied for the warmest year ever. And we wouldn't have expected to be the warmest year ever based on the state of things like the ocean and El Nino. But this small climate effect may have pushed it over the edge. The CO2 and contrail reductions would have resulted in a small cooling, but the aerosol reductions, mostly due to interactions with clouds, would have warmed the planet by changing the clouds and altering them. And the aerosols actually dominate on the short term when we're looking at something like COVID. These effects are too small to notice. They're much smaller than the weather noise. And it's critical in order to pull all these simulations out and tease out these effects, we have to think about uncertainties in our climate model estimates. And these ensembles are key to finding small signals and being able to use large computers to do it. But last thing I want to talk about is the lessons for the future. So aerosols have important impacts on the climate system, obviously. We do actually account for these aerosol impacts in our models. We expect aerosols to decrease and that to cause a warming trend in the future. We account for that in our planning for climate change and in our estimates of emissions changes. The effects of climate due to lockdowns were small. The interesting thing is there were then massive changes in aviation and transport, but this results in only small impacts on CO2. It's only equivalent to the rise over the last 10 years. The energy system did actually get cleaner. We had increased renewables. And again, one thing this shows is maybe there's a tipping point because renewables increased. The dirtier fossil fuels were not good for the dynamic energy system environment that we faced with all the changes happening. And there are higher marginal costs to those systems than the renewables. Nobody told people to use renewables. They simply shut down the coal plants because they were not efficient. It was better to use the renewables. It was actually cheaper. The other interesting thing is lockdowns are not a solution to climate change. You can stop almost all aviation and a lot of transport. You only get small reductions in climate relevant gases. We need a sustained evolution and we need to adjust our energy system anyway in ways it was already starting to get pushed due to the pandemic. What happened in Texas in February is a prime example of, we have to adjust to climate change and adapt to it by changing our energy system in important ways, not just making it climate neutral. So that's sort of an overview of the macro scale of what COVID might have done. And let me see if I see there's a couple of questions, right?
Yeah.
So I guess I can
why don't we start with the last one first?
Okay.
In terms of the arithmetic for whether simulations is it 32-bit or 64-bit?
64-bit. Most of it is still 64-bit. We are moving more and more to 32-bit because the uncertainties in things like our formulations of clouds are so large that it doesn't really matter if we're using 32-bit arithmetic or not. How does nitrogen dioxide affect weather and climate? Nitrogen dioxide is primarily an air pollutant that produces ozone. It doesn't really affect the weather. It mostly affects air pollution, but there are some climate impacts of ozone. There are small. The local air pollution impacts are much larger. And the last one, air flights have recovered to 80-90% of the pre-pandemic level. Are airlines flying empty planes to keep their planes from being idle for some reason? They're not entirely empty, but the load factors have definitely decreased. So before a plane would be 90% full, I think now they're more like 50% full. Also, a lot of that does include things like cargo flights, and those have continued. And for a while in the spring, they actually were a large part of the flight traffic because there was a lot of cargo being flown around and even more cargo being flown around. So there may actually be slightly more cargo now as well.
And then another one just came in chat asking if there's anything here to suggest that like Japan and France moving to nuclear would benefit climate.
Well, yes. So nuclear energy certainly does benefit climate because there's no carbon emissions associated with it. And that is, the fact that they use a lot of nuclear energy has been a good thing for climate. Obviously, nuclear power has other issues if it's not managed correctly, but for pure climate purposes, it is a good way. It is one way to get carbon neutral energy.
Okay, I think that's the last one. So thank you, Dr. Gettelman.